In this video, I'm going to talk about the spanning set theorem. So what the theorem says is, it begins by saying, let's let S be a set of vectors that has v1 up until vp in it. So all of those elements, v1 up until vp, they're in some vector space, capital V. And let's let H be the span of these vectors, v1 up until vp. So we've seen before, when we talk about subspaces, that the span of a bunch of vectors is going to be a subspace. So H is going to be a subspace of V. Okay, so there's two parts to what the spanning set theorem says. The first thing that it says is, if there's a vector vk in my set, in H, that's a linear combination of the others, we can remove it from S. And that's what this backslash notation means. This means S with the vector vk removed. So we can remove that vector vk from our set. And after we do that, the resulting set of vectors is still going to span H. Okay, so when one of our vectors is a linear combination of the others, we can sort of toss it out of the set without changing the span. That vector is sort of unnecessary. Okay, so the second part of the theorem is, if H is not just the zero vector, so if our subspace H is not just the zero vector, there's definitely going to be some subset of S. So some subset of these vectors, v1 up until vp, that is a basis for H. Okay, so I'm going to prove part 1 of this, and then for part 2, I'll give a sketch of the proof. Okay, so let's prove part 1. So in part 1, we want to show that when we remove the vector vk from S, that the result is still going to span H. Okay. So what I'm going to do is that I'm going to begin by saying that X, so I'm going to let X be an element of H. So if X is an element of H, so according to the definition of what H was the span of v1 up until vp. So if X is an H, well, that means that X can be written as a linear combination of those vectors. So X is going to be C1 times V1 plus ... plus CP times VP for some scalars C1 up until CP. So I'll just say for some C1, comma, ... comma, CP that are in R, that are real numbers. Okay. So what I want to show about X is that I can write X as a linear combination of these vectors v1 up until vp, but after I remove this vector vk. Because that would show that removing vk from my set doesn't change the span. Okay, so what can I do now? So the next thing that I want to say is, just to make this argument a little bit simpler, is, so I'm assuming in part 1 that there's some vector vk that's a linear combination of the others. So I don't necessarily know where vk is in my list, but I can reorder the vectors in this list if I want to. So let's just put vk at the end. So if it's not already at the end, let's just put it at the end. So what I'm going to say is, by rearranging the vi's, if necessary, let's assume that vp, the last vector, is a linear combination of the others. So v1, comma, ... comma, vp minus 1. Okay. Whoops. So that's the case, then I can write it as a linear combination of them in terms of an equation. So let's say that, let's put this in green. Let's say that vp equaled some number a1 times the first vector, plus ... plus some number ap minus 1 times the last vector, vp minus 1. And notice that I've chosen different variables here. So a1 up until ap minus 1, because I've already introduced variables called C1 up until CP. So I can't reuse those. Okay. So next what I'm going to do is, let's take this formula that we have for VP, and let's plug it into this equation up here where the VP is. So if we do that, what we get is then the vector x equals, so the first part's going to stay the same, C1 V1 plus plus, so the term before CP VP would have been CP minus 1 times VP minus 1. And then this last term is going to be CP times, and then for the VP, let's plug in what it is that we're plugging in for VP. So VP is A1 V1 plus plus AP minus 1 times VP minus 1. And notice what we're sort of getting here now is x is written only in terms of the vectors V1 up until VP minus 1 here. And then in the green, it's only written in terms of the vectors V1 up until VP minus 1. And that's what I want. I only wanted to write x in terms of those vectors. I wanted to be able to sort of toss out or discard VP. And I've done that. It's just a matter of writing this up a little bit nicer. So what can I say now? Let's just regroup the terms. So I'm going to put all the terms that have a V1 together. So what are all the coefficients of V1? Well, I see there's a C1 here. And then I see from this term over here that I'll have a plus CP. Okay, I need a little bit more room. CP A1. And that's the coefficient of V1. And if we keep going like this until the last term, I would get finally plus plus some coefficient of the last VP minus 1 here. So the coefficient of that is going to be, so I have CP minus 1. And then when I multiply CP times AP minus 1, I would get plus CP times AP minus 1. Okay, so at this point, we know that x is a linear combination of V1 up until VP minus 1. And that's the same thing as saying that x is in the span of V1, comma, VP minus 1. So x is in the span of all the vectors, but after I tossed out VP. And that's what we wanted to prove. So I'll just write as desired. That's what I wanted to show. And now we're done with the proof. So I write my done with proof symbol. Okay, so we have proved part 1 of this. For part 2, what I want to notice is, based off of what we just showed, if our set had a vector that was a linear combination of the others, I could sort of toss it out without changing the span. So the idea for part 2 is, let's just keep doing that. Let's just keep tossing out unnecessary vectors until finally I'll end up with a linearly independent set. And when I do, that set is going to be a basis. Okay, so I just need to write that down. I'm just going to sketch the proof for part 2. I won't write it up super formally, but it's basically this argument. So we're just going to keep removing vectors from S that are linear combinations of the others. And I know by part 1 that we just showed that's not going to change the span. So we're going to keep doing this until the vectors that are left are linearly independent. And once they're linearly independent, remember that the span hasn't changed, because that's what part 1 says. So at this point, they're linearly independent, and they still span our subspace, which means this is now a basis. So this is now a basis. And that's the sketch of the argument for part 2. Okay, so let's do an example. Okay, so this is example 6, and this is continuing my numbering of examples from the previous video. Okay, so let's let V1, V2, and V3 be these vectors. And I want to notice that there's some linear combination of them, it's non-trivial, that equals the 0 vector. So I'm going to use that fact to find a basis for the subspace H which is the span of these three vectors. Okay. So here's what I want to notice about this. So because I have this linear, combination that equals 0, I can use this to isolate for one of my vectors and write one of my vectors as a linear combinations of the others. So I could actually choose any of the vectors to do that with. So first, let me just do that with v3. If I were to get v3 by itself, v3 equals 2v1 plus 3v2. So that means v3 is a linear combination of the first two. So the spanning set theorem says, well, if you remove v3, because it's a linear combination of others, that's not going to change the span. So if you remove v3, then the set that we have will just have the vectors v1 and v2. So v1 and v2. And when I have two vectors, well, the two vectors are linearly independent if they're not multiples of each other. So are v1 and v2 multiples of each other? So just by inspection, just by looking at them, we can see that they're not. So this set is linearly independent since with two vectors, we just worry about whether they're multiples, and these are not multiples of each other. So this set, after I remove v3, is linearly independent. So the spanning set theorem, our argument from earlier, said, well, once I removed enough vectors to end up with a linearly independent set, well, that is our basis. So I'm going to call this script b1. So this is definitely one basis. But I also want to answer this in another way. So what if I had chosen to write my linear combination in another way? So here's another answer. Here is another answer. What if I chose to isolate v1, for example? If we isolated v1, we would have gotten 1/2 v3 minus 3/2 v2. So I can write v1 as a linear combination of the second and the third vectors. So what if we now remove v1 from our set? And if I did that, I would have the vectors v2 and v3 left over. And are these multiples? Well, v2 and v3, by looking at them, by inspection, they're not multiples. So this is also going to be a basis. Let's keep this in green. So I'll call this one b2. And this is another answer. And so it's not hard to see that if I wanted to, I could have written v2 as a linear combination of the others and removed v2 as well. And that still would have given me a basis.